Hello JChem, we're going to be looking into electrons and their specific energy levels and to describe where we can kind of find these electrons. So we know about the Bohr model and the idea that Bohr said that every electron has a certain set amount of energy. When we say set amount of energy, what we like to say is quantized energy. So every electron has a specific amount of energy. In fact, the more energy an electron has, the further away from the nucleus it is. Unfortunately, Bohr's model was a theory, and it could not explain everything about the structure of the atom. In fact, we started to learn and physicists figured out that electrons act like both particles and waves. So think of a particle maybe like a microscopic baseball, but also that electrons could move like a wave, maybe like the signal from your cell phone or water waves. So because of this, they didn't make a nice simple path circulating around the nucleus like planets orbit the sun. So because of that, we had to devise a new model. Well, electrons are pretty goofy things, so what we tried to do is instead of just making a circular path around the nucleus like this, we created what's called an electron density cloud. What it is if we can figure out where an electron is and we kind of take, if you will, for lack of a better term, a snapshot of the electrons, and you lay those pictures over and over and over and over again, you start to get areas that's a lot darker and more dense. So what we figured out was that if we look at specific electrons, 90% of the time they're found in certain specific areas around the nucleus. Now this darker area or higher probability of finding the electron led to a shape that we can assume 90% of the time the electron is found in. So we no longer think of electrons in orbits like the planets around the sun, but instead we represent it with a high probability of where most of the time this electron will be found. Now that circular picture we drew just last slide isn't the only shape, so we're going to get into that. But if you look on the periodic table, we know there are 7 periods or horizontal rows. Surprisingly, there's also up to 7 energy levels for electrons in an atom. But every energy level, which is represented also by the periods in the periodic table, they're given a number, and that number is called a quantum number. So if you're in energy level 1, you use quantum number 1. If you're in energy level 2, you use quantum number 2. Simple as that. And again, remember, the higher the energy level, the further away you are from the nucleus. Hence, energy level 1's right here, 2 and 3, and so on. Now, those quantum energy levels are the main levels, but in every main level, there can be what we call sublevels. So energy level 1 would have one sublevel, meaning one shape of an orbital. But energy level 2 actually has 2 sublevels, which means 2 different types of shapes that electrons can be found in 90% of the time. Energy level 3 would have 3 sublevels, meaning there'd be 3 different kinds of shapes that we could find electrons 90% of the time. All right, so each sublevel is still given a quantum number, which means a main number. Okay, now every sublevel is given a letter, and we're going to go through that in just a bit. So if this is a little confusing, no worries, you'll catch up here in a few slides. But every energy level is the quantum number, like energy level 1, 2, 3. But a sublevel also is a shape, and every shape is given a letter. So for example, a round circular shape would be an S. So in energy level 1, there's a 1S. In energy level 2, there's a 2S. Energy level 3, there's a 3S. Let's get into the shapes so this makes a little bit more sense. All right, energy level 1, quantum number 1, has only one sublevel, and that sublevel is in the shape of an S orbital. S is easy because it stands for like a spherical shape. So that means any 2 electrons that fit into this energy level, 90% of the time are inside this circular spherical shape. All right? Notice that we're not drawing like a nucleus with like a orbiting planet or anything like that. This spherical shape now represents where 90% of the time we believe an electron is. And again, we call that 1S. Now, energy level 2, you start to see how we build here. Quantum number 2 has 2 sublevels, which means it has 2 types of shapes that electrons can be found in. Always the first sublevel is S, the most simple one, so that's a spherical shape. So that means up to 2 electrons in energy level 2 can fit inside that spherical shape and is found in there 90% of the time. But also, since energy level 2 has 2 sublevels, it has the S sublevel and now the P sublevel. The P sublevel is actually shaped like a figure 8 or like a dumbbell shape, or I like to say almost like 2 teardrops that come together. When I go to the next slide, I'm going to show you what the p orbitals look like. All right, the p orbitals look like 2 teardrops or figure 8s, and they can be arranged in 3 different orientations. They're going to be left to right, front to back, and up and down as well. Okay, so to recap, energy level 2 has an s orbital, which is spherical, and then the p orbital can have left to right shape, up and down shape, or front to back. Since 2 electrons can fit in each of these shapes, this can hold up to 6 electrons total in the p orbitals. Okay, again, why are we learning about this? Electrons have specific energies and are found in specific places. So by knowing that, we can actually create eventually, if you will, an address for each electron to show where they are and how much energy they have. By the way, though nothing too crazy for us, the 2px, y, and z just says whether it's y left to right, z up and down, or x and y front to back. So it just tells you the orientation. Something we won't have to focus too much on. We just want you to know the shape of the p orbital. All right, energy level 3, you see that there's a pattern that's going to form. Energy level 3 is going to have 3 sublevels. So there's going to be the 3s sublevel, like energy level 1 and 2. There's going to be the 3p sublevel, like energy level 2 had, because it had 2. And then energy level 3 has one other orbital sublevel, which is called the D. So S, we know 3s is going to be spherical. P, of course, is going to be the teardrop shapes, if you will, up, down, left, right, front to back. And then D actually has 5 different shapes. So take a look. If each shape can hold 2 electrons, that's 2, 4, 6, 8. And now there's going to be 5 D ones, which is another 10. So the energy level 3 can hold up to 18 electrons. Let's get there. All right, D orbitals, though you won't have to draw these out too much, often look like 4-leaf clovers. Up, down, left, right, front, center, off to the side. But then it also makes this crazy binky-shaped one, if you will, like a pacifier. If you look dxy, dyz, dxz, all these just tell you the orientation. Again, something we're not going to have to focus on too much for this level of chem, but the idea that up to 2, 4, 6, 8, 10 electrons can be found in each of these unique shapes 90% of the time. Again, a lot different than our orbiting planet model of the atom, right? All right, energy level 4, you get the idea hopefully now. Energy level 4s is a sphere. 4p are the teardrops, up, down, left, right, front to back. The d orbitals, there's 1, 2, 3, 4, 5 of them that look like the 4-leaf clovers. And then last but not least, at 4f, the 4th sublevel is the F, which actually has 7 different shapes according to it. So let's take a look at those shapes. And again, you won't be drawing these much. These are pretty complex, but you should be able to see them and identify them if you saw a picture. And here they are. They're like double 4-leaf clovers, if you will. And again, what are these shapes? Remember, they're specific to energy level 4, and up to 2 electrons can fit into each of these shapes, which means 10, 12, 14, up to 14 electrons can be in these orbitals. All right? These shapes in that give you a brief idea of how the atomic structure is made up of now in our modern atomic theory. We do want to remind you, though, as I've been saying throughout, that only 2 electrons can fit in each shape or each of the individual orbitals, okay? Because of that, the reason is called the Pauli exclusion principle. We say that electrons, because they oppose each other, because like charges repel, they don't want to be near each other. So, for example, in the spherical s orbital, we would say that one electron is spin up and one is spin down. They would want to be on opposite sides, avoiding each other, because we know negative charges don't like being near each other. They repel. So we say that electrons in the same shape, or the same orbital shape, have opposite spins, one spin up and one spin down. And again, this is called the Pauli exclusion principle. It's important because only up to 2 electrons can fit in a shape, and if they are in the same shape, okay, the same area with 90% probability that they are found there, they want to be opposite of each other in opposite spin. Otherwise, they repel too much. All right, to sum up kind of everything that we talked about, we went over energy level 1, 2, 3, and 4. Technically, we can go even higher, right? We can go to 5, 6, and 7. But for us, up to 4 is plenty to get the idea. Remember, energy level 1 has one sublevel. It has an S. And in S, there's only one shape, a circular shape, so it can hold up to 2 electrons. The p orbitals, right, have 3 different shapes: up, down, side to side, front to back. So those 3 shapes times 2 electrons each will give you 6 total that it can hold. The d-orbital, or D sublevel, has 5 different orbitals, meaning 5 different shapes. Remember, they're like the 4-leaf clovers and all the different orientations. 5 times 2 electrons max each, because of Pauli's exclusion principle, gives you 10 total electrons. And then last but not least, F, the F sublevel, which is found in energy level 4, has 7 different shapes. That's like the double 4-leaf clover in that. And there's 2 electrons per each orbital, which means total of 14. All right, we're going to apply this information soon in order to give what we call like the address of each individual electron, to let you know where all the energy levels are, etc. But for now, this idea is getting you closer to understanding the modern atomic theory. Thanks, JChem. Have a great day.